And next we have number 8. There are 3 parts. This is part A. You are given a thread and a meter scale. How will you estimate the diameter of the thread? So we can adopt this method. We have to wrap the thread tightly as we can around the meter scale, and then we note the length of the coiled section. If the length of the coiled section is L and there are n number of turns in that coiled section, then obviously the diameter d of the thread will be d equal to L divided by n. But to still better understand what's going on, let us draw a figure. So this is how you wrap the thread tightly around the meter scale. Tightly because you do not want to keep any gap between these adjacent turns, so that the turns completely fill this length L. Now if there are n such turns, then each turn contributes its thickness to this L. And if there are n turns, and if d is the thickness, which actually is just the diameter, then d times n is equal to L. So that's how you get d equal to L divided by n. Next, in B we have a screw gauge whose pitch is 1.0 millimeter and with 200 divisions on the circular scale. And this is the question: do you think it is possible to increase the accuracy of the screw gauge by increasing the number of divisions on that circular scale arbitrarily? That is, you want to increase the accuracy as much as you want. Is that possible to do so by increasing the number of divisions on the circular scale? The accuracy of a screw gauge is measured by its least count, and the least count is pitch divided by the number of divisions on the circular scale. So yes, if you keep increasing the number of divisions on the circular scale, then the least count becomes smaller and smaller, and so accuracy increases. It keeps on increasing. The larger you choose this denominator, least count becomes smaller and smaller, and least count is the least measurement that the screw gauge can accurately measure. So if that keeps on getting smaller and smaller, so the accuracy increases. But there is a problem with this approach, and next we are going to write about that. Increasing the accuracy by increasing the number of marks on the circular scale is theoretical in nature. In practice, if you try to do that without any bound, then you face many problems. We can write one of the problems, and this is one problem. By increasing the number of divisions on the circular scale, you get the graduation marks, those marks using which you make the measurement. They become finer and finer, very fine. They are finely spaced. So after some stage, the human eye cannot distinguish between two adjacent graduation marks. But if you cannot tell two such marks apart, how will you take a measurement? So taking a reading becomes impossible after some stage. So obviously the device loses its purpose. But there are other problems also. Another problem is this: if you want to construct means if you want to manufacture a screw gauge with extremely fine marks, then the manufacturing cost will increase, because normal screw gauges cost something to manufacture. If you want to manufacture a finer screw gauge, then the equipment that you will use to manufacture it, that itself will have to be finer, more advanced, and hence more costly. And next we have part C. The mean diameter of a thin brass rod is to be measured by vernier calipers. And this is the question: why is a set of 100 measurements expected to be more reliable, expected to give us a more reliable estimate of the diameter than a set of just 5 measurements? So we have to justify this. So this is the justification. That's because when taking the average of a large number of measurements, the random errors level out. But why? Well, what do you do when you measure something? You do it with some kind of device, some equipment. Now, the equipment itself can contribute to error in measurement by being defective. So you first make sure that you get your equipment from a reputed manufacturer, so that there is no manufacturing defect. I mean, of course defects will be there, but they are not that much. Okay, so that every time you make a measurement you get something wrong, some wrong figure because of the device. That should not happen. But still the device may cause problem if you have set it up wrongly. Devices come with things that you can adjust a bit, so that you can use the device for some different purposes. So you set it up properly also, so you have eliminated the errors that may come from a faulty device or a device which has not been set up properly. These are the systematic errors. So you have eliminated systematic errors more or less. But still your measurements are going to have errors. Why? Because those errors are random errors and they are going to come from you, me. We are the sources of random errors. It's almost always the case that when you measure something with a device, there is a bit more to measure. Whatever the device can measure, it has measured, okay, and it has given you some digits which are the certain digits. But there is a little more to measure that the device cannot measure, because that is not within its least count. It is smaller than its least count. So for that, to take that into account, you supply a last uncertain digit also. Do you remember that we had these discussions back then? That uncertain digit is your guess. That is why it's uncertain. So the certain digits and that last uncertain digit together, they are the significant figures and they form the numerical part of your measurement. And on that side you have the unit. Okay. And these uncertain digits are the sources of random errors. Now we are talking about estimating the diameter of a thin brass rod, right? Say the diameter is 1 millimeter. Okay, just assume some value. You make one measurement first. You measure 1.1 millimeter. Okay, and that 0.1 is your guess. Now if you take 100 measurements like this, is it likely that every time you are going to measure 1.1? No, that is actually highly unlikely, because every time you are trying to measure, you are actually really doing your best to guess that last digit, right? It should be 0, but you are guessing only, no? You do not really know. So that if you make a large number of measurements, it's as likely for you to go a bit higher than the actual value as it is to go a bit lower than the actual value, so that ultimately when you take average, these highs and lows cancel each other, and that's how the more number of times you make measurement and use that data to take average, the more likely it is that you will be close to the actual value. So your estimate will be better. That is the reason.